Okay, let's get started to this great week of integrals. This week is going to be one of the most fundamental of this course because you're learning the fundamental theorem of calculus this week. So that's pretty fun. Okay, so hopefully everybody had a great weekend. I slept a lot. So one announcement: you have homework due tonight. You also have homework assigned for next week. You already are able to do some of it. Some of last week is bleeding into this week, and vice versa. So you'll be able to do not everything, but you'll be able to do a few things from the homework that is assigned for next week already. Okay, so but keep that in mind. Homework due tonight. Email me early. Don't email me at 11 o'clock with questions about it because I won't answer. Well, or I might answer, but you don't know. Okay, so email me early. Ask questions early. Okay, so homework due tonight. So let's remember what we were doing last time. Last time we were talking about we want to find the area under some curve. First, we're assuming the curve stays entirely above the x-axis. Okay, so this is not the last time I'm going to draw this general curve, but here's again the situation. So I've got some function. This is f of x. And I want to find this area between x equals a and x equals b. Underneath the curve and above the x-axis, okay? This is the whole situation that we're trying to accomplish. So the idea is, again, I know I sound like a broken record, but it's important to remember what the idea is. The idea is that we're going to use 1,000 or 1,000,000 or 1,000,000,000 little rectangles to approximate the area here. Okay, so instead of finding the area of some curved object, we're going to find the area of a bunch of little rectangles. And I'm going to take them so that the right edge goes up to the function. We could take the left edge to go up to the function. Or really, we could take any point in between the right and the left edge of the rectangle to go up to the function. Okay, that's actually going to be important later for proving the fundamental theorem of calculus. Okay, but I do this, and then I'm going to draw a general rectangle right here. Okay, so I'm trying to fit in rectangles in here. Oh, do we have questions? Oh, okay. It looks like we got worked out. All right. So we're trying to fit in rectangles into this area, right? So that means if I'm taking the width of all the rectangles to be the same, which you don't have to, again, we're doing this in a very specific way. You can do this in a much more general way, but it's much easier to do it in a specific way, okay? So if I take all the rectangles to have the same width, well, I'm trying to fit in rectangles into a length of b minus a, right? I'm going from x equals a to x equals b. So that means that I should take the width of all these rectangles, delta x, to be b minus a. I'm trying to fit in things into a length of b minus a. And if I come down here and I start labeling these points, there's x1, there's x2, there's x3, blah, blah, blah. Here's xk, where I've taken k steps away from a. Well, then xk is going to be, what was it? Who remembers? Or who can work it out from this? I'm taking k steps of delta x away from a. So what is xk then? What? Yeah. A plus K times delta X. Perfect. Perfect. So there's XK. So then if I want to find the area, which I'm going to represent in blue, if I want to find the area of just this one general rectangle, well, the area of any old rectangle is just its length times its width, its base times its height. Whatever words you want to use, you take one side and you side length and multiply it by the other side length, right? So the side length for this general rectangle, the base, well, that's delta X. And the height, well, we're using right endpoints, but we could just as easily use left endpoints. But either way, the height is going to be one of these 2 points up here. And right now I'm taking it to be f of xk. All right. So we can say the area, the red area, is approximately, well, if I take all of these rectangles and I add up their areas, well, what would that look like? Well, the area of one rectangle is f of xk times delta x, right? That's the area of that blue rectangle. But that's just a general rectangle. So all the rectangles have this area that looks like this for changing k. And then I just let k equals, well, I'm starting with this first rectangle where I'm going up to f of x1, right? So I'm starting with k equals 1. I'm ending my last rectangle is k equals n. Okay. So this is the approximate area under the curve for any fixed n. So that's a lightning fast recap of what we did last week. All right. So then the idea is, if I want to find what's the red area, not just approximately, what is the red area? Well, what do I do? If I use 10 rectangles, this is a decent estimate. If I use 100 rectangles, it's an even better estimate. If I use 1 billion rectangles, that's a pretty darn good estimate. What am I describing right now? I'm letting n get bigger and bigger. What is that? Do we have it in the chat?
Are you taking a limit?
Yeah, exactly. I'm describing taking a limit as n goes to infinity, right? I'm letting n get bigger and bigger and bigger and bigger. That's just looking at the limit as n goes to infinity of this sum. Well, that is the red area. Okay. And so as a reminder of this sigma notation, this means you let k equal 1 first, and then you add when k is equal to 2, and then you add when k is equal to 3, and so on and so on and so on. Okay. All right. So we could actually technically, in order to do this process of taking this limit, f needs to satisfy a few conditions. So instead of this being the definition of the area under the curve, it's technically a theorem. We're not going to worry about the technical hypothesis. As long as f is continuous and non-negative on this interval a to b, so again, that means it lies above the x-axis, then the limit as n approaches infinity of both the left and the right hand sums exist and are equal to each other. And they both are equal to the area under the curve. Okay, so this is the right-hand sum. Right-hand sum. And this is the left-hand sum. There's very little difference between the two. The left-hand sum, instead of using the right edge of the rectangle going up to the function itself, we use the left edge of the rectangle, and that goes up to the function. Okay, so that's the only difference between these two. This right-hand sum is also called a right Riemann sum. Okay, this is these are both Riemann sums. Question in the chat. Ah, yes. All right. So any questions on this? I sort of just showed, again, it wasn't technically approved, but hopefully it was convincing. Are you guys convinced that as that the sum of those areas of rectangles is going to give us the area under the curve when we take a limit? Is everybody convinced? It's proof enough for me then. All right. So again, just a quick recap of the notation. Delta x, it's b minus a over n, and x I here, or xk, I was using a k before, so I'll change these to k's really quick. K. Okay, so those are sort of the two, those and the function itself are the most important things when you're trying to actually compute these. We're not going to actually compute areas under the curve for very complicated functions, okay? Because it's quite annoying. We're going to learn a simple way to do it. I'm not, on the homework, you'd have to do 2, I think, and they're not anything more than a quadratic function, okay? So let's do an example to see this in action. I'm going to change this I to a K again. Not that it really matters, but for consistency. All right, so we're going to find the exact area under the curve y equals x squared between x equals 1 and x equals 2 and above the x-axis. Okay, so this is a new problem for a lot of you. Okay, the problems before where we were finding exact areas, it was with like straight lines, things that you knew already. This is a genuinely new problem. Presumably, if you haven't taken calc before, you've never seen the area under a curve, under a parabola. I mean, circles are probably the most curvy objects you've found an area under. Okay, so first, I always like when I'm doing these. This is a Riemann sum problem. When I'm doing these types of problems, I still like to draw out what's happening. I know I just did it, but I'm going to do it again, and you should too. Okay, so let's get a quick map of what's going on here. Here's an x, here's a y. We're going from x equals 1 to x equals 2. It doesn't have to be an exact drawing. It just has to be good enough. Okay. And so x squared, well, that goes from 1, 1 to 2, 4. It's a parabola, so it's something like that. It's a little curvy. Not too curvy, slightly curvy. All right, so we're trying to then, someone tell me what area am I trying to find? I'll draw in a few dashed lines here. Here's a dashed line that might be of interest. Here's a dashed line that might be of interest. What area am I trying to find here?
The polygon below the curve?
Yes, below the curve. So all of that? Is it all of that?
Only the positive.
Yeah, I'm being stupid, right? It's below the curve, but above the x-axis. Okay, so below the curve, above the x-axis. And so do we want all of this? This feels like Blue's Clues. I'm sorry. No, we want everything between those dashed lines, right? Below the curve and above the x-axis. Okay. So it's important to be able to draw the region that we're trying to find the area under. Now, it's not always going to be so explicitly given to you. Okay. Sometimes the question might be phrased as find the area that's bounded by two curves. We're going to tackle a problem like that later. Okay. We don't have the tools quite yet to tackle that, but it won't always be so explicitly given to you, just so you know. So it is important to be able to draw it. All right. So I'm going to draw a general rectangle. And let's use a right hand sum, because that's what I've been doing so far. Again, there's really, as far as the area is concerned, there's really no difference between the left and the right hand sum. All right, so I'm starting at 1, and then over here, my right edge, I'm calling xk, the x coordinate there, okay? So I need to know a couple of things about this rectangle, right? I need to know what is its width, delta x. I need to know what is its height. Well, now for Riemann sums, we're just using n rectangles. N is some variable, or not a variable. N is some unknown thing. It's fixed to start, but n is some unknown thing to us, okay? So then what is delta x? The width of that rectangle.
1/n.
Good. How did you get that?
You take your second point minus your first point and then put it over n.
Good, good. Yeah, we've got an interval here. The whole length of the interval is 2 minus 1, which is 1. I'm going to divide that by n rectangles I'm trying to fit in here. Okay, so delta x is 1/n. Very good. Okay, so then now I need to know what is xk. Well, again, remember, xk is when I've taken k steps away from my left edge. So it's always going to start with your left edge, 1 plus, then what am I going to put next?
K/n.
Perfect. K/n. In general, it's k times delta x, but for us, delta x is 1/n. Okay, so k/n. Very good. So then the only other thing I'm going to need to know is what is that height, f of xk? Well, what is that? You don't need to expand it. Just tell me what it's going to look like at first. Have it in the chat. Yeah, you just take xk and you square it, right? F of x is x squared. So I'm going to take xk and I'm going to put it in parentheses when I square it, because you do need to FOIL this eventually, okay? So then the area, the red area, is going to be equal to, well, first my approximation is just the sum k equals 1 to n of f of xk, so that's 1 plus k/n squared times delta x. Well, that's 1/n. Okay. There's my approximation, and then I'm going to take the limit as n goes to infinity. Okay. Questions on that? Now, I said we're never actually going to compute anything super complicated. I might have you set up one of these on an exam. I might have you set up one of these for a very complicated function, but not evaluate it. Okay. So by that, I mean, I would just have you write this out, but not actually take the limit or find the sum. All right, so let's actually start working this out because we actually can do it for this function. This is the limit as n goes to infinity. 1 over n, does that depend on k at all? No, as far as the sum is concerned, as far as this big sigma is concerned, 1 over n is a constant with respect to k. Okay, so you can pull that out in front of the sum. You can't pull it out of the limit because the limit is depending on n. Okay, so this is 1 over n times the sum, k equals 1 to n. And then I'm going to expand 1 plus k over n squared. Well, that's going to give me 1 plus 2k over n plus, plus k squared over n squared. Okay. Questions on that so far? Got a question in the chat? Cool. All right. So, do I need to add a page? No, I left myself some room. Good job, Chase. All right, so this is equal to, well, let's come back. Remember, with the sum, this sum just works like sums you're used to. You can break it apart into each of its individual pieces, okay? So this is equal to the sum, well, first of all, the limit as n goes to infinity of 1 over n, that's still out there, times. First, we have the sum, k equals 1 to n of 1. That's that first part. Plus the sum, k equals 1 to n of 2k over n. And then plus the sum, k equals 1 to n of k squared over n squared. Okay. Questions on that? On what I did there? Okay, what is this first bit right here? The sum k equals 1 to n of just 1.
N,
What was it?
just n.
N, yes, perfect. This is the limit as n goes to infinity, 1 over n times. Yeah, if I add 1 n times, that's going to give me n, right? So this is just n. Plus this sum. This is one of those special sums. First, I'm going to pull the 2 over n out. 2 over n doesn't care about k. So 2 over n times the sum k equals 1 to n of k. What's the sum k equals 1 to n of k? Who remembers? Ooh, so close. Yeah, you were close enough that I'm going to say good enough. This is n times n plus 1 divided by 2. Very good. And then plus, so I'm just going to do plus 1 over n squared times the sum k equals 1 to n of k squared. I'm going to write that one down on the next line. No one ever remembers it, and that's fine. On an exam, I would give you this formula. Okay, so this is going to be equal to the limit as n goes to infinity of 1 over n times n plus 2 over n times n plus 1 over 2. And then plus 1 over n squared. The sum of k squared from 1 to n is n times n plus 1 times 2n plus 1 divided by 6. Okay. Questions so far? All right, so I would not, now that we're actually taking the limit, before if I just said what is an approximation for n rectangles, I would probably want you to simplify this. But now we're taking the limit, and with the limit, we can break things up piece by piece, just like with the sum. Okay, so the only simplification I'm going to do first is distribute this 1 over n everywhere. Okay, so when I do that, I'm going to get the limit as n goes to infinity of 1 over n times n. Well, that's 1. And then 2 over n times 1 over n, that's going to give me plus 2 over n squared times n plus 1 divided by 2. Plus, and then 1 over n cubed times n plus 1 times 2n plus 1 divided by 6. Okay. All right, so now then, we can do a little bit of cancellation, a little bit of simplification, but we don't have to get everything under the same denominator, is the point I was trying to make before. Okay, so this is the limit as n goes to infinity of 1 plus 2 over 2 is going to cancel there, right? I'm going to be left with n squared plus 1 when I distribute the top. Or sorry, plus n when I distribute the top of that second term, n squared plus n divided by n squared. Okay, so there's that second term. The third term, well, there's going to be a little bit more work. You're going to be left with, what, 2n cubed plus 3n squared plus n divided by 6. Questions so far? And how did I get those? Just expand each of these.
Is not that 6n cube?
What was it?
Is not that 6n cube?
Oh, thank you. Yes, the bottom is, yeah, I forgot that n cubed out in front, over 6n cubed. That's very important. Thank you very much.
Also, for the second term, can you cancel 1n?
You can. I'm not going to worry about that. You can definitely do that if you want, but it's all going to come out in the wash in the end when we take the limit. So let me add one page. I don't think it, yeah. Add a page. So last thing we need to do here, let's look at the limit as n goes to infinity of just 1. Well, that's this first part. So what's the limit as n goes to infinity of 1? 1, exactly. So the first part of that sum is just 1. What's the limit as n goes to infinity of n squared plus n divided by n squared? Oops, sorry. Who remembers? Yeah, these are rational. This is a rational function where the degree of the top equals the degree of the bottom, right? So what do we do for this limit?
Isn't it also just 1?
It's also just 1. Yeah, perfect. We take, this is 1n squared plus n divided by 1n squared. So I take 1 divided by 1. Well, that's also going to give me positive 1. Very good. And then the last bit of this limit, the limit as n goes to infinity of 2n cubed plus 3n squared plus n divided by 6n cubed. What is that going to give me? 1/3, exactly. Again, we have a rational function where the degree of the top, 3, equals the degree of the bottom. And so we can just divide the term or the coefficients on the n cubed. We get 1/3 here. Okay, so the limit, I'm just adding all these up, right? The left-hand side is the limit of the big sum that I cared about. The right-hand side, the final answer is going to be 2 plus 1/3, 1 plus 1 plus 1/3. Times 3/3 is 6/3. So that's what, 7/3. And if anyone's taken this class before and has seen the fundamental theorem of calculus, which we've done, we're going to do this week, you'll know the easier way to get this answer, but you'll notice that we get the same answer as the easy way. Okay, so this is using Riemann sums, the limit definition of, well, we're going to find out what is called the definite integral. Okay, but this is the area under the curve. That is the red area there. Okay. So in theory, you can find areas under any functions. It's annoying for you currently. It's annoying to do, but you can do it. Do we have any questions about this at all? Like I said, there's two problems on the homework that are like this. One is a linear function, one is a quadratic function. So what we just did is the most that you'll have to do as far as these sums go. All right, another example. Find the exact area under the curve y equals the square root of 1 minus x squared between x equals -1 and x equals +1 above the x-axis. Okay, hint, maybe we don't need rectangles on this one. So my advice, 100% of the time, when you're trying to find these areas, get a sketch of really for 99% of calculus problems, get a sketch of what's going on. Okay, so a sketch of what's going on. Well, what does this curve look like? Who knows? It's okay if you don't know. Well, in order to see what's really going on, let's do a little bit of manipulation. I hate the square root, right? Let's get rid of it. Let's get rid of the square root. How do I get rid of the square root? I can't just throw it away, but what can I do to both sides? I can square both sides. That'll get rid of the square root. I'll have a y squared, but that might be a little easier to work with. Okay, so if I square both sides, squared, I get y squared equals 1 minus x squared. And then if I add x squared to both sides, I get x squared plus y squared is equal to 1. And what's that the equation of? Yeah, that's the equation of a circle with radius what? Radius 1, perfect. So x squared plus y squared is the circle of radius 1. However, we started off with just y equals the positive square root of 1 minus x squared. So we shouldn't have y be below the x-axis at all. So really, we only want the top half of the circle of radius 1. Okay. So this question is asking us, find the area of really half of a circle of radius 1. Oops. Half. Okay, well, what's the area of a circle? Just first of all, a circle of radius 1. What's the area of that circle? Who remembers? It's not 2 pi r squared. It's pi r squared for the full circle, right? So pi r squared for the full circle. What is r for us? 1. So pi for the full circle, but how much of a circle do we have here? Half. So what should I do with pi? Divide it by 2. Very good. So in a few slides, you're going to see what's called the definite integral. I'm going to tell you, when you guys learn the fundamental theorem of calculus, you're going to completely forget about this example, but this is one of my favorite examples to give in all of calculus, because it's easy if you remember what the integral is. It's hard if you try to use this theorem we're going to learn in a few slides, okay? So keep this in mind if ever this comes up on an exam. I almost guarantee that this will come up on an exam, this exact example, okay? So any questions on this? Cool. All right. Find the exact area under the curve y equals 3 plus x between x equals 0 and x equals 2 above the x-axis using the limit of a sum of rectangles. I'm going to do this after class. I want to get to this next slide. So if I have time, I'll come back to it. But I want to move on to this slide first, okay? So, so far we've only been talking about graphs of functions that lie above the x-axis, right? We've been looking at things where it makes sense to call this region, it makes sense to find the area of that region, okay? But we could have just as easily, if I'm looking at a function that I'm going to draw in blue, if I'm looking at some other function that does something like this, well, it would have been just as easy for me to say that the blue area here is positive, and I'll just call the green area underneath the curve, I'll just call that negative, right? I mean, that seems to make sense. If the curve lies below the x-axis, well, then I'll say that's not adding to the area that I'm finding, that's taking away from the area that I'm trying to find, because the function is negative there, okay? So this is the idea of assigned area. If a function lies above the x-axis on some interval, the area underneath it is positive. If the function lies below the x-axis, the area underneath it is really above the curve, is negative, okay? In trying to find the area of this function, the signed area of this function, we wouldn't do anything different. Nothing that we have done so far would change. We would just say, we would draw in a bunch of rectangles, right? Here's a bunch of rectangles. And then down here, then we just have rectangles that come down to the curve instead of going up to the curve. But notice when we do this process of finding this width, delta x, and this function height at, we'll call this xk, well, f of xk down here, f of xk, is it going to be positive or negative? It's going to be negative, right? This is going to be less than 0, and delta x, we're always taking to be positive. So when we do this process of adding up all the areas of a bunch of small little rectangles, these rectangles, they're going to take care of themselves as far as the sign of the area is concerned, right? Because when I find the area of this rectangle, I'm going to get delta x times f of xk, just like we did before. This is positive, and this is negative. So when I find that area of a rectangle corresponding to where the function is below the x-axis, I'm going to get a negative area, okay? So this isn't really new. We're just extending the idea of area to signed area. So we could have 0 as an area under the curve. We could have negative areas under the curve, and that's totally fine now. Okay. So when I'm talking about the signed area under a curve, and really when I'm talking about, this also applies for when I'm only talking about positive areas, then we use the following notation. This is, you read this as the integral from a to b of f of x with respect to x. Okay, this is the area, really the signed area under y equals f of x between x equals a and x equals b. Okay. So, because nothing would change in finding this, then we're going to, oh, sorry, this is called the definite integral of f of x from a to b. It's called definite because, well, we'll see why in a minute, but notice we use the same symbol that we did for indefinite integrals, right? That's not an accident. They are related, and we're going to see how they're related when we talk about the fundamental theorem of calculus. Okay, so because when we're calculating this signed area, nothing would really change. We still draw on those rectangles, then take a limit as n goes to infinity when I add up all the areas. The definite integral has the following definition. Okay, this is nothing new. This is just the left and right Riemann sums when you take the limit as n goes to infinity. Okay, so, but now we just have this fancy symbol that really just means signed area under f of x. So I don't have to keep using a highlighter to indicate what this sum is. Okay. So are there any questions about these definitions here? Or really this one definition? They both give you the same thing. Okay, so again, the first definition, this is using I is starting at 1, I or k, whatever index you want to use. It's starting at 1 and ending at n. These are the right hand, it's the right Riemann sum. These rectangles use the right edge to go up to the curve. Okay. The second definition, that's the left Riemann sum. That uses the left edge of the rectangles to go up to the function. Is there a difference between them? Not functionally. They're going to give you the same answer when you find the area under a curve, the signed area. Okay. Okay. So just as a reminder, these Riemann sums, we're adding up a bunch of areas of rectangles and then letting the number of rectangles go to infinity. That's all we're doing. So the definite integral is defined by a limit, right? The limit as n goes to infinity of that sum, of those Riemann sums. We've seen limits that don't exist, right? We've seen limits that go off to infinity, or limits that bounce back and forth between two numbers really fast. We've seen that happen before. So we're not guaranteed, it is not guaranteed that the integral from a to b of f of x with respect to x is not guaranteed to exist. Okay. And if we're thinking about the area underneath the curve, can you think of maybe a function where the area underneath the curve might not exist or might be infinite? Who can think of a curve where the area underneath it might be infinite? Let's get those brain juices flowing. Rational functions, yes, that's a good place. That's a good idea to start. So what specifically about, there's a pretty simple one that's gonna give us an infinite area. So in order for the area to be infinite, what has to happen, you think? Because if I'm just looking at some function from, let's make it as a hint, let's make it the integral from -1 to 1. If I'm just looking at some nice function, well, that pretty clearly is going to have a well-defined area. What has to happen for the area to be infinite?
It has to be non-continuous.
Yes, perfect. That's exactly right. And so what's one way a function could be discontinuous or non-continuous? Discontinuous is the technical term. Specifically, one way that will maybe make the area blow up. Yeah, perfect. An asymptote, right? If we have a vertical asymptote, that's blowing up there, then the area, this isn't a proof. This isn't a proof. You can actually have asymptotes where the area actually is finite. Integrals are weird, guys. They're very weird. But in this case, if you're looking at the function y equals 1 over x squared, and you're trying to find the area underneath it between -1 and 1, that's infinite. It doesn't, you would write that the integral doesn't exist, okay? So this example shows that you're not guaranteed at all that the integral exists. But as was pointed out, this function is special because it's discontinuous. If you have a continuous function, then you actually are guaranteed that the integral is going to exist. So this is a theorem. Again, I'm not really going to prove it. The proof isn't that bad. It's just dealing with a lot of the Riemann sums. And I mean, nobody likes those. Okay, so, and it's not really enlightening. So really the thing you need to remember is that if you have a continuous function on an interval a to b, then finding the area underneath that is always going to be a well-defined problem. Okay. Any questions on this? All right, so some other special properties. That again, the proofs just require you to write out a ton of Riemann sums. If you want to see them, I can write them out for you, but they're very tedious and very boring, and again, not very enlightening. Okay, so if f of a exists, then the area underneath f of x between x equals a and x equals a, well, that's 0, right? That one's pretty easy to see if you just draw. Here's a. I mean, here's f of a. I mean, what is the area underneath? What's the area of just a line? It's 0, right? That's the proof of that one. Okay. And then number 2 is a little weird. The integral from b to a of f of x is equal to -1 times the integral from a to b of f of x. So this is saying, this is actually one case where you would, your delta x, when you're looking at the big sum, your delta x would actually be negative. And that's really where that negative comes from on the right-hand side. Okay, so the takeaway for number 2 is that if you swap the bounds of integration, and that's what those are called, the a and the b are called bounds of integration. Oops. Bounds of integration. So if you swap the bounds of integration, then that's fine, but you need to put a negative out in front of the integral if you do that. Okay. So there are a few more properties that we're going to look at. Again, it just comes from looking at the big Riemann sums. So we're going to pick up here tomorrow, and then we're going to, I think tomorrow we'll be able to get into the fundamental theorem of calculus, which is very exciting. Okay, so if anybody has any questions, I have office hours today. You can stick around and ask me in here. But other than that, please feel free to head out after you wipe down your desks. And thank you everybody for being here.
Thank you.